section 612 is titled Pythagorean Triples. So how can I use similar triangles? So yesterday when we were talking about triangles, we pointed out that triangles when you have angle-angle similarity, they can follow a pattern. For the 30, 60, 90, that one's a special one. And for the 45, 45, 90, that one's a special one. So if we see either of those, we can determine their side lengths based on their special ratios. Question number 12 says, use the tools you have developed thus far to determine the lengths of the missing sides of the triangles below. If you see a pattern that can be used, share it with your team. Be ready to share your strategies with the class. So the very first one we see in A has an angle measure of 60. It's one of the special ones that we learned about yesterday, the 30, 60, 90 triangle, where if you know the hypotenuse, you can get the short leg simply by dividing by 2. If you know the short leg and you want the hypotenuse, you would do the inverse, which is to multiply by 2. So in this case, you take the hypotenuse of 12, divide it by 2. That gives you a short leg of 6. Okay? To get the longer leg, you would take the short leg and simply multiply it by radical 3. Okay? They don't want it as a decimal, they just want it as a simplified radical. Okay? There's no calculator even involved in this because most people can divide by 2 or multiply by 2 easily. Okay? All right, for part B, it doesn't say that it's a 45, 45, 90 triangle, but it has this side marked with a tick mark and this side marked with a tick mark, which automatically makes it a 45, 45, 90 triangle, which means that both the legs are congruent. So if this leg is 3, then C is also going to be 3. And then the hypotenuse of a 45, 45, 90 triangle, you're simply going to take the leg and multiply it by rad 2. It's just one of the special patterns that we learned yesterday. Okay? That always works on a 45, 45, 90 triangle. So if you see a 30, 60, 90, it's going to follow this pattern. You see a 45, 45, 90, it's going to follow this pattern. For triangle C, it doesn't say, or we don't know that it's either of those two special patterns. The only thing we know about it is that it's a right triangle. So for the right triangle, we can use the Pythagorean theorem. The Pythagorean theorem says that the hypotenuse squared is going to be equal to the leg squared plus the other leg squared. So we're just going to calculate this one out. 3 squared is 9. 4 squared is 16. Added together, that's 25. Then we take the inverse operation of squaring, which is square rooting, and that's going to make the hypotenuse 5. This one in particular is going to end up being what we call a Pythagorean triple. Okay? Any questions on problem A, B, or C? All right. Let's move down to D, E, and F. All right. So for D, we're going to notice that D follows the pattern of problem C that we just looked at. This side is 6, which is double of 3. This side is 8, which is double of 4. So the hypotenuse we said was 5. That means side F, we're going to double it, and side F is going to be 10. Can you put your phone away, please? You're going to put your headphones and your phone all the way in your backpack. Right now. All right. For part C has this angle marked at 30, which makes this a 30, 60, 90. So to find the hypotenuse, we can take the short leg, which is 4, and just double it. Most people can multiply this in their head. 2 times 4 is just 8. Then we take the short leg and we multiply it by the square root of 3 to get the length of the longer leg. For question F, it's not a 30, 60, 90. It doesn't follow, it's not a 45, 45, 90, and it doesn't follow a special pattern yet. So we're going to use the Pythagorean theorem on it because it's a right triangle. So that we're going to say that the hypotenuse I squared is equal to this leg squared 5 squared plus the other leg of 12 squared. This one you might need a calculator, but most people can do this in their head. 5 squared is 25. 12 squared is 144. Add those two together to get 169. And then the square root of 169 is 13. This, which one is this? F, triangle F is actually going to be also one of our Pythagorean triples. Okay? Any questions on D, E, or F? All right, let's look at the last row down here. Triangle G. Triangle G looks really huge. It has 3,000 here, 4,000 here. But if you realize that it's just the same as problem C, just multiplied by 1,000. Okay, if you look back up at C, this short leg was 3, the longer leg was 4, and the hypotenuse was, what was the hypotenuse up on C? 5. So we're going to take the 5, we're going to multiply it by 1,000, which means that the hypotenuse on this one is 5,000. We don't even need a calculator for that because it follows that special pattern. Okay? Triangle H. Triangle H is like triangle F that we had up here where we had 5, 12, and 13. If we look here, we would just multiply the short leg by 3. We would multiply the longer leg by 3. So if we know the length of the hypotenuse is 13, we can take it and multiply it by 3 to get a ratio of 39. And the last triangle I doesn't follow any of those patterns. It's the only thing we know about it is that it's a right triangle, so we're going to use the Pythagorean theorem on it, which says that the leg squared plus the other leg squared equals the hypotenuse squared. So 9 squared is 81. 41 squared, you probably need the calculator for this one. It's 1,681. We're going to subtract the 81 from both sides, which gets us 1,600. And then we take the square root of both sides, and we get a longer leg of 40. This one is also technically going to be one of our Pythagorean triples. Okay? Any questions on G, H, or I? Anybody still writing? Okay. Give you guys a minute to catch up there. Number 13 says, Carl noticed some patterns as he was determining the side lengths of the triangles in problems 6 through 12. He recognized that the side lengths in parts C, D, F, G, H, and I were integers. He also noticed that knowing the triangle side lengths in part C can help determine the hypotenuse in parts D and G. Groups of numbers like 3, 4, 5, 5, 12, 13 are what we call Pythagorean triples. If you have a highlighter, go ahead and highlight that. If you don't, circle it and put a star. Pythagorean triples are super important. It says, why do you think they are called Pythagorean triples? It's because they describe integer side lengths of a right triangle. There aren't decimals, there aren't radicals. They're nice, pretty numbers that we call integers. Okay? So part B says, what other sets of numbers are also Pythagorean triples, and how many different sets can you find? The most common ones that you'll see over and over are the 3, 4, 5, If any of you have ever worked construction, this one is super commonly used in construction so that the corners of your buildings are perfect right angles. Otherwise, your buildings would be wonky, okay? And 5, 12, 13 is pretty common. 7, 24, 25 are most common. These are less common, but you will see them sometimes. There are technically many, many more, okay? In your teams of 4, you are going to do problems 14. You're going to look for 30, 60, 90 patterns, 45, 45, 90 patterns, or any that are multiples of your 3, 4, 5, 5, 12, 13, or 7, 24, 25. Okay?